half of the book deals with kinetics from observation, empirically. So we derive things like the rate law, etc. The second part of the book deals with it from a more theoretical point of view. And so we can also derive the rate law, not based on experimental data, but we could derive the rate law from a theoretical perspective. So that's what we're going to look at. Now, and so from a theoretical perspective, what's happening when we have a reaction is there's a collision. And so they call this collision theory here. In collision theory, there are two important aspects to this. One is you have to have a collision, and that collision has to have enough energy to break bonds. Two, that collision has to have the correct orientation, that is, to form the new bonds that we need to form. And so if we take a look at these three collisions down here, the top one's successful because the molecules have the correct orientation and they have the correct energy. And so the the O bond here, the NO bond is breaking, and then we're forming a new bond, the NO bond over here. So what we're going to do is we're going to take N2O and NO to form N2 and NO2. So a lot of collisions don't have enough energy. They might have the correct orientation, but if they don't have the correct energy to break those bonds, then no reaction is going to result. So if we go back and take a look at the Maxwell-Boltzmann thermal distribution, or the kinetic energy distribution curves here, we'll see that at, let's say, T1, there's a small fraction of high energy molecules, and then there's going to be a cutoff. This cutoff is going to be the energy required to break and form new bonds. That's called the activation energy. The stronger the bonds, the higher the activation energy, the smaller the population. The weaker the bonds, the lower the activation energy, and the greater the population. So we shift this left or right, the cutoff here, depending on how strong the bonds are. Now, it's not based entirely on bond strength, because breaking bonds cost energy, but forming bonds releases energy. So there's some cost and benefit in this. And so, typical covalent bonds, single covalent bonds, are around 300 to 400 kilojoules per mole. The activation energies are usually less than that, because it's not just breaking bonds. So, in food has very low activation energies. Food, let's say if you have something in 200, maybe 300 kilojoules per mole, food is going to be under 100, more like 50 or 60 kilojoules per mole. And that's because you really, when you're cooking food, you aren't always breaking the bonds. Sometimes you're just breaking hydrogen bonding interactions, which hold the proteins in their correct shape. And so you denature the proteins. And so food having relatively low activation energy gives it some unique characteristics. That is, one of the characteristics of the kinetics of food is for every 10 degrees C temperature increase, you double the reaction rate. And so things cook twice as fast. But that's only for low activation energies. If you have higher activation energies, then that rule of, and this is a rule I learned in intro chem, doesn't hold true. And so for things like food, it works. This food has activation energy around 60 kilojoules per mole, which is pretty small. Now, you might have the correct energy, but if you have the incorrect orientation, then nothing's going to happen. And so these are unfavorable collisions. So we need a combination of enough energy, that is, an energy greater than the activation energy, and the correct orientation. There are other aspects to collision theory. There's a lot more to it. Things like collision frequency. How many collisions per second are there? And out of all those collisions, which one do you think is collisions per second? Maybe something like this, 10 to the 32 per second or so. Out of all those, how many are going to have the right energy, and how many will have the right orientation? It will be a much smaller number. And so all these numbers are significant in terms of the kinetics. Some of the numbers are, what is the distance the molecule travels before it collides? It's called the average difference is called like mean free path. And so we have things like mean free path, collision frequency, etc., wrapped up in those numbers, but we aren't going to pay attention to it too quantitatively, except to say that the rate if the collision's probability is high and the activation energy is not so big, then the rate's going to be fast. If the probability of the collision is low and the activation barrier is high, then the rate's low. And so this is what we call a simple collision. So if we track this, the N2O plus NO yields products into NO2, what happens is we end up breaking bonds and forming bonds. And this state here where this bond's breaking and this bond's forming is called a transition state. There's a transitory state in going from reactants to products. We can't isolate this. In fact, this is so short-lived. This is on the order of 10 to the minus 15 seconds, femtoseconds. That's how fast this reaction occurs. In fact, this is a very rapid reaction. And so if this reaction happens in 10 to the minus 15 seconds, if you try to track the progress of this reaction, you need something that probes this even faster than that. And so what you need is what's called a femtosecond laser. A femtosecond laser gives pulses every femtosecond, or faster. Like a picosecond laser is too slow. If you have a picosecond laser, you shine light here, and then by the next time you shine light on this, the reaction's already done. So all you see are the reactants and products. You don't see the transition state. In order to see this transition state, you need something that's very, very fast. And the reason is when you shine light on this, it's going to give you a different absorption spectrum than if you shine light on this, than if you shine light on this. So you'll see changes in the absorption spectrum from shining light on these species. And so 10 to the minus 15 is femto, 10 to the minus 12 is pico. It used to be the technology was picosecond lasers. And so with a picosecond laser, you can observe slower reactions, but for something like this, you need something quite fast. Now, normally in thermodynamics, we just look at the reactants and the products. So this would be exothermic. Delta H is equal to minus 139. But in kinetics, we look at how it gets there. How does it get from reactants to products? Well, first there has to be a collision. This collision has to have enough energy. And so it's got to make it all the way to the top of the hill. Not only that, it has to have the correct orientation. So very few of the population here will make it over the hump here to form products, unless you give them some boost. Energy. All right, that's called a simple collision. And when we have a simple collision, then the kinetics are pretty simple. But we'll come back to this soon. Now, we can represent that mathematically. In terms of the collision frequency and the probability that collision occurs, that's given by this term A. This is our Arrhenius equation. The Arrhenius equation tells us the rate constant. The rate constant is equal to A. A is called the pre-exponential constant, or the frequency factor. And that just tells us, how probable and how frequent those collisions are, because if they're probable here, then A is big. If they're improbable collisions, then A is small. And so it will be, A is usually determined experimentally. But you can try to determine it theoretically by looking at the probability of those types of collisions occurring statistically. And then E to the minus EA. EA is the cutoff energy, the activation energy. The larger the activation energy, the slower the reaction. The smaller the activation energy, the faster the reaction. Okay. And temperature. Temperature gives us the thermal distribution. The higher the temperature, the faster the reaction. The lower the temperature, the slower the reaction. And so this is the Arrhenius equation, which kind of incorporates what we just talked about in terms of collision theory into the rate and how fast it occurs. Now, there are different forms of the Arrhenius equation. So that's the one of them. The next form is if we take the natural log of both sides. If we take the natural log, then we're going to get ln of k is equal to minus EA over R, 1 over T, and will be our x variable, plus ln of A. Okay. In this form, this is the y equals mx plus b linear form of the Arrhenius equation. And we can make an Arrhenius plot. And so what we do is we measure different rate constants at different temperatures. And so here, if you have a bunch of rate constants at different temperatures, then you can plot them in an Arrhenius plot. From the Arrhenius plot, the slope will give us the activation energy, so we can determine the activation energy experimentally. And then we can also determine the frequency factor A from the intercept experimentally as well. And so this is typically what's done here, determining the activation energy A. If we only have 2 data points, then we don't need to do a full Arrhenius plot. The nice thing is if we have lots of data, we can average that data by just doing a linear least squares fit. But if we only have 2 data points, then 2 data points will define the line. It's going to be more susceptible to error, but it'll be simpler. And if we only had 2 data points, what we'll do is we'll take ln of k at temperature 2 minus ln of k at temperature 1. So using property of logs, we'll get ln of k2 over k1 is equal to minus EA over R 1 over T2 minus 1 over T1. So here, if we know what the activation energy is, and we know the rate at one temperature, we could figure out the rate at any other temperature. And so for food, we can increase the temperature by 10 Kelvin, and we can see the rate double. That is, K2 will be twice K1, roughly. That's because the activation energy is fairly low. The other way this is used is the rate is inversely proportional to the time. And so rather than represent these as rate constant, we can represent these as time. So this is T1, this is T2. And this is going to be minus EA over R, 1 over T2 minus 1 over T1. So the time could be, how long did it take? Or it could be half-life, any time you can use there. Oh, the B term, it cancels out. And if you go through the Zoom, the homework Zoom, I'll derive this equation.
Is it ln T1 over T2 or ln T2 over T1?
T1 over T2. So this is a common trick that we do. We'll take ln of K2 minus ln of K1. This is going to equal, well, K2 is going to be minus EA over R, 1 over T2. And ln of K1 is equal to, okay, so this is going to be minus EA over R, 1 over T2. Oh, plus, I forgot the plus ln of A. Plus ln of A here, plus ln of A. But A is the same for both of these. And so this is going to be plus ln of A minus ln of A. And so the ln of A is canceled. And then we end up with this equation here. And that's what happens. So going back to a simple collision like this, the rate laws is easy to derive because this is just a one-step collision. And so if we had a one-step collision like this, if we double one of these, we'll double the number of collisions, which should double the rate. And so if we double both of these, then the net effect would be quadrupling the rate. And so we have, whenever we have a reaction, we have 2 possibilities. So if I have AA plus BB plus ... goes to product. The 2 possibilities are, this is just a simple collision. There's one step. Simple collision is just one step. And And that step is called an elementary process. And we're going to go through some transition state, and then we'll go to product. And therefore, the rate is just equal to K, A to the little a, B to the little b, dot, dot, dot. And so it is whatever, we call this the molecularity. And so it depends on how many molecules. If we had one molecule of A, then it would be first order in A. So if we double A, then the reaction rate should double because we'll have twice as many collisions. If we have two molecules of A and we double A, then we double one side, let's say the left A, and then we double the other side, which is the right A, so we actually quadruple. And so that would be it. The other possibility is that there are hidden steps in here. Hidden steps. That is, it doesn't occur as one simple collision, but there are multiple collisions that happen. And in that case, if there are multi-step, we call this a mechanism, then the rate is not simply the molecularity of the overall reaction. The rate depends on the slowest step. And so in there's going to be one step that's going to be slower than all the other steps. And this one step that might be slower than all the other steps is going to be called the RDS, the rate determining step. So let's say this is the slowest. It doesn't matter how much faster these are, as long as they're faster. The slowest step dictates the rate, because everything has to pass through that slow step, so it dictates the rate. But we don't know what the collision is involved. So each of these arrows represents a simple collision. So what's the collision involved here? Since we don't know that, then we can't predict what that's going to be. So we'll just say that the rate is equal to K, A to the N, B to the N, etc. Where M and N are derived from the slowest step in the mechanism. So these are related to the slowest step in the mechanism. The slowest step in the mechanism is called the RDS, rate determining step. So since we don't know if this is a simple one-step process or a multi-step, we just treat it as multi-step. We treat it as multi-step and then do it this here. Otherwise, we have to be told. So, for example, if we look at the combustion of methane, methane combusts to form CO2 and water. The water somewhere here. And so methane plus oxygen yields CO2 and water. There are many more steps, high molecular compounds go on here. In fact, there are hundreds of steps in the combustion of methane. And there are a whole bunch of, these are not transition states, these are what we call intermediate products. The transition states are these transitory things where we're in the process of breaking bonds and making bonds. But here, once we've done that, for example, we broke a bond here, and we're left with CH3, which is called methyl radical. This is a product. And in between going from here to here, there's a transition state to observe. But anyway, the situation here is the reaction is much more complex than just a simple one-step collision. And in this complex mechanism here, there's a slow step. And that slow step is going to dictate how fast the overall reaction occurs. But, which one of these is that the bottleneck? in this reaction. Okay, so that's what we're going to be looking at in this part. So we have different types of elementary processes. This one's called unimolecular. Unimolecular because it just consists of one molecule. And when we think about collision theory, that one molecule of A collides with something. What does it collide with? It collides with the wall of the container, or it collides with an unreactive molecule like nitrogen. And so there's a collision of A with the wall or an inert molecule. And what that does is it transfers or kinetic energy into potential energy in the collision. That potential energy can yield product. But this is very simple. If I double the concentration of A, I'm going to double the number of collisions, which doubles the rate. Right? I'll have twice as many collisions with the wall if I have twice as many molecules of A. And so it being a simple elementary step or elementary process, the rate is just equal to Ka to the first. However many A's I have one A. Collides. Let's say I'm looking at a collision like this involving two A's, a left A and a right A. Here, the rate is going to depend on the concentration of the left A and the concentration of the right A. So I'll separate them out rather than calling it A squared. I'll say A on the left, A on the right. If I double the concentration of left A, that's going to double the number of collisions that occur with the left A. But if I'm doubling A, then that is going to double both because they're both in the same container and they can't differentiate between left and right. And so in this case, if I double A, I'm going to quadruple the rate, so it's second order in A. If I have a bimolecular, this is called a bimolecular collision because it's two molecule collision. If I have an A and a B, I can double A, that's going to double the rate. And if I double B, that will double the rate. And so if I double both A and B, that's going to quadruple the rate. And so it's first order in A, first order in B, and second order overall. So if I double everything, I expect quadruple. And so the most common elementary processes or collisions are going to be unimolecular and bimolecular. These termolecular collisions are much rarer because in this case, these two A's, all three A's have to collide at the exact same time. So let's say I have this middle A, then this left A has to come in and the right A has to come in at the exact same time. So if I have the middle A, then the two A's have to coordinate their collision and collide in the exact same moment in time. How probable is that? Well, it's not very probable, And so this is like being sandwiched here. Or like a B. B has to be sandwiched by two A's right at the same instant of time. And so the two A's must be communicating with one another, maybe to coordinate the collision. Or it just happens by chance. If it just happens by chance, it's not highly probable. The same thing here. This B has to be sandwiched between the A and the C at the exact same instant of time. You can't have B being in a collision with A and then subsequently after that have it in a collision with C. No, it has to be all at the same time. And so the probability is low. It doesn't mean it can't happen. It can happen. It's just slow. Low probability. So you'd expect it to be slow. So if we look at this reaction goes from A to C. And going from A to C, there are hidden steps in it. It's just not A goes to C. In this particular reaction, the hidden steps, there are two steps. There's one hump here. This one hump corresponds to a simple collision. The simple collision is it has to collide with enough energy in the right orientation. If it collides with enough energy in the right orientation, then we form a transition state in which bonds are breaking and bonds are forming. And then that transition state can break down into a product here. But this is not the final product. This is what we call intermediate product. And then the intermediate product has to undergo a collision, in this case a unimolecular collision, with enough energy and orientation to form this transition state, which can fall into product here. And so this is what we call a two-step mechanism. And so for this particular reaction, all these are one step. How do we know? How we know is because we're told they're elementary processes. If we aren't told they're elementary processes, then who knows how many steps these are. And therefore, we can only use M and N. If we're told these are elementary processes, then we know that there's nothing hidden, and we can use A and B for the coefficients. The coefficients as exponents. This is a paper from 2016, the chemical kinetic modeling of methane combustion. And what they have a detailed kinetic mechanism, including 213 elementary reactions and 48 species from the literature. And then lots of branches here. And so, even though there are only 213, there are many, many branches, many, many different paths that it can go. Yeah.
So, in regard to the crystal violet lab that we did, would you say that lab had like 50 steps in it, or?
Yeah. That I would say had hidden steps. And therefore, we could only call it M and N. Versus if it just happened in a single, simple collision. Maybe it does. If it happens in a simple single collision, then it should be first order in crystal violet and first order hydroxide. Maybe that's what you got. So it could be just a simple collision. Let's take a look at this one here. So in this particular reaction, we have H2 plus 2 ICLs. So if this were to happen in one simple collision, one single step, then we have to have a coordinated collision of 3 molecules in the exact same instant of time with the correct energy and orientation. And so that's low probability for one, but it could happen, it's possible. I mean, there's no other choice. However, they determined the rate law for this from experiment. And so the experimentally determined rate law, it shows it's first order in hydrogen and first order in ICL. If this were a simple collision, then it would be second order in ICL, because it would depend on 2 ICLs. Let's say the left ICL and the right ICL. It would depend on those concentrations. Okay. And so what we can say is this doesn't happen as one simple collision here. They're hidden steps. And so what would be more likely is either unimolecular or a bimolecular collision. Those are much more probable. A unimolecular would be a collision with a wall or some inert molecule. So if hydrogen collides with the wall, what do you think happens? Do you think it just breaks apart? The 2 hydrogen atoms? No, probably not. Probably hits the wall, bounces off. The same thing with ICL. If ICL hits the wall, maybe not. So let's not look at unimolecular. Yeah, it's more likely it's a bimolecular collision. If it's a bimolecular collision, then let's take a look at that. So we have an H and an ICL. So one thing is they have to have the correct orientation and energy. So if they collide, maybe this is what happens. Maybe the HH bond starts to break and the ICL bond starts to break here. At the same time these are breaking, new bonds are forming. Maybe an HI bond and an HCl bond, like that. And so this would be called a transition state here. Transition state is where bonds are being broken and new bonds are being formed. In transition state, we don't isolate because it happens so fast. It's hard to isolate. But what's going to happen is this transition state can drop down into a product. And so what do you think the products we're going to form from this collision will be? Probably HI and HCl. So this forms what we call an intermediate product, and that is HI. HI is not present in the reaction there, but if we take the HI and react it with another ICl here, then what we can form, HI and ICl would form what? Do you think? If we have HI and HCl, maybe I'm going to put the HCl like this, and the H here. What do you think I can form? Well, HI and HCl can form an HCl and an HI. Well, it's the same thing. So we got to think of what else it might form. Oh wait, this is, yeah. What we probably should do HI and ICl. Let's try that. So if we do an HI and an ICl, what can we form? Well, we can form another HCl and an I2. And then we have this HCl from before, so we'll have another HCl here. And so at the end of this, we'll have two HCls and an I2. So that's what we expect here. So there's a hidden step here in this. This reaction doesn't happen in one step. This reaction is looking like it happens in two steps. The first step is a collision of one H2 with one ICl, not two ICLs. That would be a bimolecular collision going through this. This would be the transition state here, and then it would drop down to the products. The products of that first step would be HI and HCl, HI and HCl. Then we have one more ICl left over. That one more ICl that's left over can react with the HI to form I2 and HCl, so giving us altogether two HCls. Now, these humps aren't even. For the first one here, it requires more energy, and so that has a higher activation energy. If it has a higher activation energy, it's going to be slower. K will be slower. The second step here has a lower activation energy, so this will be faster. And so the first step is the RDS. If the first step is the RDS, then what does the RDS depend on? The RDS just depends on the collision of HI and ICl. And so this is the mechanism that is proposed. Step one. H2 plus ICl yields HCl plus HI. This we're going to call slow. If this is the slow step, then the rate is going to depend on this step. Since it's an elementary process, it's just going to be equal to K1, we'll call this K1, times the H2 concentration, times the ICl concentration. It is, but the second ICl doesn't react in step one. The second ICl reacts in step two. So if we move on to step two, we're going to have HCl. Oh, no, not HCl, HI. HI react with the second ICl. That is, this is the HI here. And this is going to be given by K2. K2 is faster. And what results here is an HCl plus an I2. It doesn't matter what the rate is. You know, the rate is going to be dictated by the bottleneck, and the bottleneck is the first step. And so what we see is that the rate of the RDS, the slowest step, is this. When we measure the rate from experiment, we get the same rate law. So the experimentally determined rate law matches the rate law that we got from the mechanism here, the hidden steps of this. And so this agrees with experiment. And then the net reaction here, the HI is what we call an intermediate, and that cancels out. And so we end up with H2 plus 2 ICLs yields 2 HCl plus an I2. So the net reaction agrees. So if both of these agree, then what we can say is, therefore, this is a plausible mechanism. A plausible mechanism just means that this could be the correct mechanism. Or it means that, well, maybe this is a contributing mechanism of other mechanisms. There could be another mechanism that also agrees, or multiple mechanisms that also agree. And so in order to determine if this is the mechanism, then we'd have to maybe look for HI. HI, we don't need a femtosecond laser for. You know, HI is a product, it's fairly stable. And so we could just use a normal spectroscopy, not this high-speed spectroscopy that we would need for transition states, because HI is not a transition state. HI is what we call an intermediate product. Intermediate products are fairly stable, and those can be determined. So if we determine that there is HI being produced in this reaction, then that leads to further evidence that this might be the mechanism for this reaction. I don't know if it's the one and only, because when you look at something as simple as methane combustion, it's not so simple. You know, it's quite complex. But this is a plausible mechanism. Yeah. So the rate is going to be determined by the slow step. And so when we're dealing with mechanisms, at least in this chapter, we have two scenarios. One is the first step is the biggest hump, the biggest hill to climb. And so if you're riding bicycles, you know, the rate that you're going to go from left to right here is going to depend on this biggest hill. You know, how many people can make it over that speed, that is. If you're going, you know, you're all going single file. This second hill is nothing compared to the first hill. The other possibility is that the second step is the slow step. Okay, we aren't going to get any more complicated than that. So, one, the first step is a slow step. Two, the second step is a slow step. And that's what we're thinking for this one. This is nitrogen monoxide or nitric oxide and oxygen. Nitric oxide is a colorless gas, and it's rapidly oxidized by oxygen to NO2, which is a brown-orange gas. And so this reaction happens very quickly. The rate law was determined from experiment, and it was found to be second order in NO and first order in O2. So what it looks like is it could be a term molecular collision. That is, the rate depends on both NOs and an O2. But since this reaction happens so fast, intermolecular collisions are so low in terms of probability that this doesn't look like a simple collision. There's probably some hidden steps in here. And so what we can do is we can propose some alternate, maybe plausible mechanism. So one plausible...
I'm lost. I'm not gonna lie. I'm lost right now. How do we determine the slow step?
The slow step is given usually. You don't really determine it, because you could determine it using thermodynamics to see what the energies are. And that is what, in fact, that's what you can do using Spartan, which is a quantum mechanical program. In Spartan, they have things where you can generate transition states and determine their energy. And then based on the energy of the reactants and the energy of the transition states, the one that has the biggest climb is going to be the slowest step. And so that way you can determine it. Otherwise, we're going to have two options. The first step is slow or the second step is slow. And so this one we don't know, but we can try different mechanisms here. One, we could try unimolecular mechanism. And so if we look at this here, is a unimolecular one very probable. Let's say NO hits the wall, or O2. When O2 hits the wall, does it break apart? No, it just kind of bounces off. When NO hits the wall, is it going to break apart? Probably not. I mean, it's a triple bond. It's a nitrogen-oxygen triple bond. It's pretty strong. I don't think it's going to break apart. So I don't think the unimolecular is very favorable. Maybe bimolecular. So if we have bimolecular, we have two different choices. If we have bimolecular, then what we can have is, let's say, two NOs colliding or an NO and an O2 colliding. So let's try an NO plus an O2 colliding. What do you think that might form? Yeah, well, we don't have enough for an N2. NO3? Okay, NO3, one thing we might try to do is draw the Lewis structure for NO3. Nitrogen's 5 electrons, oxygen is 6, times 3 is 18, plus 5 is 23 electrons. So far I've used 24 electrons, so I have to get rid of one. What that makes is a free radical. Free radical, we have unpaired electrons. Not only that, nitrogen doesn't have an octet, so probably want to make a double bond here for that. Something like this. And then we're going to end up with some formal charges here, a positive formal charge here, a negative formal charge there. And that's as close as we're going to get. Does that look very stable? No, it's going to be pretty reactive, but that's all right. It could be pretty reactive. What else might we form here? Or we might form something like NO2 and O, atomic oxygen. Is atomic oxygen very stable? No. Atomic oxygen would be very reactive. It doesn't have an octet, it wants an octet. So it's going to be very reactive. But, this is very reactive also. What else could we form? Well, NO2 is okay. That's just a single and a double. We'll have a resonance form for that. It's still a free radical. NO2 is going to have a single electron here, double bond, single bond, like this. And so it's going to be odd. 1, 2, 3, 4. This is going to be plus, this is going to be minus. So we can generate a low structure like this, and there's going to be a resonance form for this as well. What else? How about this? Somebody might propose this, an N and an O and an O and an O. Does that seem very stable to you? No. I mean, this would be ridiculously unstable. All these would be free radicals, and all these wouldn't have an octet. This would have 5 valence electrons. This would have 6 valence electrons. Be quite unstable. So this one, let's eliminate that one. How about this one? Maybe a nitrogen radical, atomic nitrogen and an ozone? Maybe. And so these are all possibilities that we think of when we're generating the mechanism. Alternatively, we might not have a NO and an O2. Let's have two NOs collide. And so we'll say, or If I have two NOs collide rather than an NO and an O2, what could I form? N2O2, the molecule? N2O2. N2O2, can we draw the Lewis structure for that? And so if we draw N2O2, how many electrons do I have? 2 nitrogens, 10, 4 oxygens, 4 times 6, 30. Oops, that's N2O4, that's wrong. N2O2. Well, N2O2 is a little bit better, perhaps. Let's go like this. So when I look at this, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. 22 electrons. You got 10 electrons here, 12 electrons here, 22 electrons. In N2O2, everybody has an octet. Are there any formal charges? No, all the formal charges are 0. So this looks like a good stable structure, okay? N2O2. In fact, N2O2, since it's a stable structure, we expect to be able to define N2O2. Somebody must have made it. It has a weird name, dioxohydrazine. That's one. Or N-oxonitrous amide is another. But, you know, there are other names for it. Structure, description, molecular weight, etc. Dinitrogen dioxide even has its own Wikipedia page. Here. So this is another possibility here. What are some other possibilities? Some other possibilities would be, you know, or maybe this, N2 plus O2. What do you think of that? This is good, except there's a problem. Because what I have is an NO plus an NO plus a O2. And so the next step must be an O2 plus an N2 plus an O2. And so in other words, the next step I'm going to have an N2 plus 2 O2s. What am I going to form there? Well, N2 and O2, that's air. And air is stable. Does the nitrogen and oxygen in air react? Not at room temperature and atmospheric pressure. And so this is going to lead to no further reaction, because this is a stable mixture. This is like air. Stable mixture, which is fine, but that's not our product there. Or how about this one? Or we could go N2O plus O. N2O is fine. That's called nitrous oxide, laughing gas. And then we form atomic oxygen. Or we might have done this. We might go NO2 plus N, atomic nitrogen. When it comes to stability, I'd expect atomic nitrogen to be more stable than atomic oxygen. You know, oxygen's more electronegative. It really wants that octet. But looking at all these possibilities, which one looks like the most promising in terms of stability and in terms of further reaction. This one here. And so I think out of all these, we're going to eliminate this collision because it just doesn't produce anything. And we'll focus on this. And so this will be step one. So step one, we have a bimolecular collision that generates N2O2. So that would be an NO plus an NO yields N2O2. Okay, now N2O2 is not one of our products. Our product's an NO2. And so there's got to be another step here. Step two is taking the N2O2 and reacting it with the other reactant. The other reactant we haven't used yet is O2. And so what do you think forms here? N2O2 plus O2 would form maybe N2O4, but N2O4 can break apart into two NO2s. And so we'll leave it like that and then see if this works out. Well, N2O2 is what we call an intermediate species, the gas, and that will cancel out. And so the overall net reaction is two NOs plus an O2 yield two NO2s. And so the net reaction checks out. And therefore, it's plausible based on that, but we have to look at the rate law. Now, if we call the first step slow, what would the rate law be? If the first step were slow, the rate law would be rate is equal to K NO squared. Does that match with what's seen in an experiment? No. And therefore, the first step can't be slow. What about the second step? If the second step were slow, the rate would be equal to what? Yeah, it'd be K times the N2O2 times the O2. Does that match with experiment? Well, actually, the answer is we can't tell. We can't tell because we have the intermediate product. Intermediate product is not allowed in the rate law. So intermediate product is not allowed in the rate law. There are two ways to get rid of the intermediate product. One way is the steady state approximation. Two ways to fix. One is the steady state approximation. The second way is a simplified version of the steady state approximation. And the simplified version of the steady state approximation is called the fast reversible. First step. So what I want to do is I want to do the fast reversible, the simplified way first. So if I go back to step one is NO plus NO. It's fast and reversible, so I'll drill 2 arrows like this. It's going to yield N2O2. For the forward rate, we'll call it K1. The reverse rate, we'll call K minus 1. And so in the fast reversible simplification, what we do is we say that the rate of the forward reaction is equal to the rate of the reverse reaction. And so the rate of the forward reaction is just K1 times the NO squared. The rate of the reverse reaction is K minus 1 times the N2O2 to the first. And then what we do is we solve for N2O2, the intermediate. So we solve for this, so that we get the N2O2 is equal to K1 divided by K minus 1 times the NO concentration squared. Then what we'll do is we'll substitute that in to the rate law from the RDS. So the rate from the rate determining step is equal to K times the N2O2 times the O2. And we're going to substitute it in here. So we're going to get K. It's actually going to be K2 in this case. That was step 2 of step 1. So K2 times this. K1 over K minus 1 times the NO concentration squared times the O2. And then what we're going to do is we're going to combine all the constants and just call that K. And so we'll get K NO squared times O2. And so the intermediate, formation of the intermediate depends on the NO squared. And so this is what we end up with here. And so the rate law from the mechanism agrees with the rate law from experiment. And so this agrees with experiment. Agrees with experiment. Therefore, this mechanism is plausible. However, there could be other mechanisms that are plausible as well, so we're not going to worry about those. We have a plausible mechanism here. So again, the fast reversible, we look at the first step and say the rate of the forward is equal to the rate of the reverse. And that allows us to substitute in N2O2 there. The other way of doing it is the steady state approximation. So that's one, steady state approximation. So when we look at the 2 steps here, if we look at step 1, NO plus NO yields N2O2. In the fast reversible, we say any N2O2 produced goes back to NOs, and any NOs go back to N2O2. So we have this equilibrium happening here. We have this equilibrium, but step 2 could upset that equilibrium by Le Chatelier. And that is N2O2 can be leaked out here to form 2 NO2s. And so here we have K1, K minus 1, K2. And so if we're losing N2O2 to step 2, then that means not all the N2O2 goes back in the reverse direction here. In the fast reversible, we assume all the N2O2 goes back. You know, this is an equilibrium here. But in reality, not all the N2O2 goes back, as in the fast reversible. Some of it leaks out. Now, the fast reversible is okay. This is valid if K2 is small. If K2 is small, then the amount of leakage here is minimal. So if we think of this as step one as being a balloon, then there's a tiny, tiny pinhole leak. And so the balloon's going to maintain its equilibrium here, but this tiny, tiny pinhole leak, some of the N2O2 is going to leak out here. But we can't always assume that the leak is very small. That is, if the leak were more significant, then we're going to lose a lot of N2O2 here. And we aren't going to have a complete equilibrium here. There's going to be a Le Chatelier's type shift. Do you see that? Here. And so in the steady state approximation, we define it differently. What we're going to say is the rate of production, rate of N2O2 production, is equal to the rate of N2O2 consumption. In the fast reversible, the only consumption was the reverse of the first step. In the steady state, we're going to have consumption due to K minus 1, the reverse, and K2. And so the rate of N2O2 production, it's only produced in one way. This one's not reversible. And so that's going to be K1 times the NO squared. Okay, this is going to equal the rate of N2O2 consumption. Well, N2O2 consumption is going to happen by K minus 1. So that'll be K minus 1 times N2O2. And it's also going to be due to K2. So this is going to be plus K2 times the N2O2 and the O2. The first. So these are the two ways it's going to be consumed. And so this is going to equal N2O2 times K minus 1 plus K2 times the O2. So here it's being produced and it's being consumed in two ways. The reverse is step 1 and step 2. Now we'll solve for this one, N2O2. When we solve for the N2O2, we get that the N2O2 is equal to K1 NO squared divided by K minus 1 plus K2 O2. Then we substitute it back here. If we substitute it here, we're going to get a slightly different equation than what we just generated here. So let's bring that over here. And so what we're going to end up with is the rate of the RDS is equal to K, okay, now I'm going to plug this whole thing in here. It's K1 over, or NO squared over K minus 1 plus K2 O2. Okay, and then this is going to be times the O2 concentration here. Okay, so simplifying this, what we get, we'll just leave it like this. This is K2. We'll give us K2, K1, and O squared times O2 divided by K minus 1 plus K2 O2. All right, so if K2 is very small, if K2 is very small, then this pinhole leak, this is our balloon, and this is our pinhole leak. Pinhole leak is very, very small. So if K2 is small, then that means this term here is going to be small. And then, therefore, we'll use the simplifying assumption. The simplifying assumption is if K2 is very small, then this term is negligible compared to this term. And so this term disappears. And then if K2 is very small, then the rate law is the same as we get from the fast reversible. Do you see that? So fast reversible is good if the second step is small. However, if the second step is significant, then this term doesn't drop out. And if this term doesn't drop out, let's say K2 is bigger than this, what happens is this term might drop out, and then this cancels, and we're left with second order. But based on the observed kinetics, it's got to be that K2 is small. And that's why we get that equation there. Let's look at enzyme kinetics here. This is the proposed mechanism for enzyme kinetics. The proposed mechanism for enzyme kinetics is that in the first step we have the enzyme here. Enzyme is actually a biological catalyst. We'll talk more about catalysts later. But what a catalyst does is it provides an alternate mechanism, a lower energy pathway, so a smaller activation energy. So without catalyst, the substrate, which is the reactant, has to break this bond here. The substrate breaks this bond and forms products. So there's going to be some collision there and break that bond. However, if there's an enzyme present, there's an active site in the enzyme which tugs and pulls on the atoms of the substrate. And what can happen is it can pull and stretch this bond. That is, it puts a tensile stress on there. And so it pulls this side this way and this side the other way, it weakens that bond and makes it easier to break, and therefore lowering the activation energy. So in enzyme kinetics, we have two steps here. And it's thought as the second step is the slow step, the RDS. The second step is the slow step. That means the rate of the RDS is equal to K2 times ES. ES is the enzyme substrate complex. ES is also an intermediate, so we can't have an intermediate there. So there are two ways to get rid of an intermediate when the second step is slow. What are the two ways of getting rid of the intermediate? Fast reversible or steady state. Now, the kinetics of this don't always agree with the fast reversible. And so what we should do is we should do the steady state approximation, because the steady state will give us a more general equation. So the rate of production of product depends on the second step. K2 is the slow step. And so the rate of production, that is the rate of reaction, is equal to V. V stands for the velocity, which is the same as rate, which is equal to K2 times the enzyme substrate. Well, we can't have an intermediate. So we got to get rid of the intermediate. And so what we do is we invoke the steady state approximation. In the steady state approximation, we say that the rate of formation of intermediate is equal to the rate of consumption of intermediate or destruction. And so how's the intermediate formed? The intermediate's formed in step one. Here. And so the intermediates form from E and S. So the rate of formation would be K1 E times S. So the rate of formation is K1 E S. First order E, first order S. So if we double E, we get twice the rate, twice the collisions. If we double S, we get twice. However, consumption is going to occur two ways. One is the reverse. Now, if we did fast reversible, it's only the reverse. But we could also have some leakage here in the second. And so consumption is going to come out two ways. One, it's the reverse of step one, or two, it's step two. And so this is the consumption, the reverse or step two. Now, if this are fast reversible, then we assume that K2 is very small, negligible, and ignore K2. But this is not fast reversible. This is steady state. Now, for enzyme kinetics, we're going to do one more thing. For enzyme kinetics, the one more thing we're going to do is we're going to look at what we call the free enzyme concentration and the complex enzyme concentration. So the free enzyme plus the complex enzyme is going to give us the total enzyme concentration. The total enzyme concentration is equal to the amount of enzyme you dumped in there at the beginning of the reaction. So you dump in a whole bunch of enzyme, and then some of it's going to complex and some of it will remain free. And that's given by these two. And so we're going to have the initial enzyme concentration, which is going to equal the free enzyme concentration plus the complex enzyme concentration. Okay. Then we're going to solve for the free enzyme concentration and substitute here. And so the free enzyme concentration is equal to the initial enzyme concentration that you dumped in there minus the complex. So this is the total enzyme minus how much is complex gives you the free enzyme. And so that's what we're substituting here. So we're going to do two substitutions. One here, and so we're going to get the free enzyme concentration as this. And then two, we're going to solve for ES. When we solve this equation for ES, we end up with this equation here. And then we do something funny with the K's here, and that is we call Km the inverse of this, K1 down here, K minus 1 here, and K2 here. And so we can throw a Km there, and then over here we can get rid of the K1s. They'll cancel out. Actually, I go through this derivation and zoom more. But after doing the substitution, okay, so we did three things that are kind of different here. One is we get it in terms of total enzyme. Two, we do this funny thing with the Ks. And three is our standard. We just substitute the intermediate. And so this is the intermediate. We plug that into our equation here. And the rate is equal to this. It looks somewhat similar to this one that we just derived over here. Somewhat similar. But the way that this works is like this. You know, if the substrate concentration is very small, what that means is you have plenty of enzyme. If you have plenty of enzyme, then and you're a substrate, then you have no problem. There's plenty of enzyme to go around. And so this is an analogy of this would be, well, phones. If there are plenty of phones, then, you know, like cell phones. The analogy used to be pay phones. If there are plenty of phones, then it doesn't matter. You could have twice as many people who want phones, they'll get it. There's a phone for everybody because there are plenty of phones. And so the phones would be the enzyme. And so what that means is this. You have plenty of phones. Therefore, if you double the number of people that want a phone, they'll all get it. You can make twice as many phone calls. If you triple it, everybody will get it. And everything will triple. The rate triples. The rate being the number of phone calls. But pretty soon, you're going to run out of phones. You know, you just put a fixed amount of, maybe phones isn't the best analogy, but you have a fixed amount of phones, and pretty soon you don't have enough phones. So people are going to have to start sharing. And so what that's going to mean is this. Everybody wants to make a phone call, but there's not enough phones, so you're going to have to wait your turn. And so what's going to happen is we could double it from here. Let's say you've already maxed out, all the phones are being used, and now all of a sudden you double the number of people that want to make a phone call. Are you going to make twice as many phone calls? Let's say you have 1,000 phones, but now you have 2,000 people. Are you going to make 2,000 calls at the same time? No. Or if you quadruple it, you know, if you have 1,000 phones and now all of a sudden you have 4,000 people, are you going to make 4,000 calls? No, at the same time. And so what happens is we run out of enzyme. And so it's fine up to a certain point, but once you get to high substrate concentrations, we run the risk of running out of enzyme. And the enzyme is how much you dump in there to begin with. So you either got to dump in more enzyme or you're going to just have to wait. And so this is a very famous equation called the Michaelis-Menten equation from 1913. And what this says is if the amount of substrate is small, that is, the concentration of substrate is small, then this term drops out, because this would be the simplifying assumption. Km plus something that's negligible is just equal to Km. And if that's the case, then the rate of the reaction depends only on S. The amount of enzyme you dump in there initially, yeah, it's going to depend on that, but that doesn't change. You know, enzyme's a catalyst, so... and so what we see is it's first order in S. So if we double S, we'll double the rate. If we quadruple S, we'll quadruple the rate. But eventually, if the substrate gets very high, then we start running out of enzyme. If this is big, then the Km term drops out. So if S is very big, then these two S's cancel out, and then the rate just depends on how much enzyme you have in there. And so it becomes zero order in S because there's no S in there. That is, once we top out here, it switches to zero order. And so this shows the Michaelis-Menten. At low substrate concentrations, high enzyme, then it's first order in substrate. At high substrate concentration, then it becomes zero order because it doesn't matter how much extra you add, you've already maxed out all the enzyme. And you aren't going to speed up the reaction anymore. Does that make sense here? And so this is the Michaelis-Menten. It's first order, down low, zero order up high for reactant. The reactant is substrate concentration. All right, let's take a break now. Let's go for like a 10-minute break. Is that enough? All right, a 10-minute break and then we'll start up again to that.